We're adding more tools to our toolkit now in algebra. The next piece is going to be equations where we have a squared or a cubed variable. And here are two examples of squared and cubed variables. So that would be like this g here. It's not just a regular g, it's g squared to the power 2, another way to say it. Same thing here as a j, and it's cubed to the power 3 is another way to say that. So we're going to deal with equations like this. And in order to do that, we need to invoke another algebraic inverse operation, right? What I'm saying is we have inverse operations in algebra, like add and subtract. Remember, they're the opposite. They undo each other. Multiply and divide undo one another. In order to undo this square here, in order to get rid of the 2, we need to use what's called square root. And in order to get rid of the 3, the cube, we would have to do the cube root. So we're going to tackle those ideas here in this video. So we're really just going to deal with perfect squares and cubes to start with. They're nice, well, they're perfect because, and the reason we call them perfect is because they work out to nice numbers. Like we have here 1 squared. Remember what that means in math is it means that there's that exponent of 2 means that there are 2 1s being multiplied together. So that's the same as writing 1 times 1. Well, of course, that's 1. You know, work your way down, even this 5 squared at the bottom, 5 to the power 2, that's the same as writing 5 times 5. So that brings us to the 25. When it's a power of 3, like these cubes in the second one here, if you had 1 to the power 3, remember what that means is it means 1 times 1 times 1. Don't add them, multiply them, so 1 times 1 times 1 is still 1. You know, 3 cubed would mean 3 times 3 times 3, 3 to the power 3. Means that there are 3 3s. That gives us 27. Again, don't say 9, we're not adding them. It's not 3 plus 3 plus 3, it's 3 times 3. Well, 3 times 3 is 9, and then you times 3 again, so that brings us to 27. Now, in order to go in the reverse direction, we need to do square roots and cube roots. So to do that, all we do is we take our number and we say, well, if we want 25 to undo it, to bring it back to the 5, then we do square root of 25. That gives us 5. The square root of 9 brings us back to 3, right? It's just taking the statements here and kind of running them the opposite way. How do you go from the 25 back to the 5? Well, you do this thing called square root. Square root is asking, in a way, it's saying, what number, when you multiply it by itself, gives you this thing under here, right? Square rooting a number. Let's say I even picked a gross number like the square root of 18. And I don't know what that is off the top of my head. I'll run it in on my calculator here real quick. And I get a number that's close to 4.24. It keeps going on my calculator. But what that's saying is 4.24, when you multiply it by itself, gives you 18. That's what square root does. It kind of says what number, when you multiply it by itself, gives you that number. So that undoes squaring, square root. To undo cube root, to undo cube, we have cube root, and that looks very similar to what we just did. But the cube root symbol looks the exact same, but it has a little 3 out here to say it's a cube root. So for example, the cube root of 8, looking back at our list of perfect cubes up here, is 2. Because what it's asking, again, just like the square root, the cube root is asking what number, when you multiply it by itself 3 times, gives you this number under the root symbol. Right? How am I going to get to the 8? What am I going to multiply by itself 3 times? Well, the only way to get there is to go 2, right? Because 2 times 2 times 2 is 8. 2 times 2 is 4. 4 times 2 is 8. So that is how we get to 8, is we need 3 2's multiplied all together, right? Same thing if we had the cube root of 125, that would be 5. Because what number, when you multiply by itself, 3 times gives you the 125 here underneath? Well, it's 5. 5 times 5 is 25, and then another 5 brings you to 125. So we're going to use this idea of squares and square roots, cubes and cube roots, to help us tackle equations that have squared and cubed variables. So here's the example from the first slide. We have 3g squared plus 18 equals 66. So we're going to tackle this problem exactly as if that little 2, that little square in the corner, was not there. So if that was gone, if I just covered it, what would we do first? Well, we'd get rid of the 18, right? We'd say, how do we get rid of plus 18? We subtract 18. So let's work through that process. And we'll just rewrite the 3g squared for now. Plus 18. And what do we do to both sides? We subtract 18. On the left-hand side, the 18's eliminate, so we're just left with 3g squared. On the right side, we have 66 minus 18. 66 minus 8 would be 58, and then 10 would be 48, so we have 48 on the right-hand side. Again, we'll just ignore that the 2, we'll just pretend that this 2 is not here. And what would we do next? Well, we divide both sides by 3, just like we normally would. So we go through that process. On the left side, we are left with our g squared. And 48 divided by 3, that is 16. Now, everything we've done so far is just the same as we would have done before. The new step that we're adding in, this new idea that we're adding in here, is we want to get g by itself. But it's not by itself right now because it has this square up in the corner. Well, what's the opposite of squaring? How do we get rid of something? Is we got to do its opposite. Well, what's the opposite of squaring? That would be to square root. So we square root the left side, and because we got to follow the rules of algebra, we do the same thing to the right side. We square root it as well. Now, on the left, the square and the square root symbol, those cancel each other out. That's how we get g by itself, right? Just like, I want to just take a second and look back. Just like add 18 and subtract 18 canceled one another out, just like multiplying by 3 and then dividing by 3 down here canceled each other out, this is the exact same idea. Squaring and square rooting cancel one another out, so it helps to get our variable isolated. Okay, and on the right side, the square root of 16, that's a perfect square, 16. So what number, when you multiply it by itself, gives you 16? Well, that would be 4, because 4 times 4 gives us 16. So that means g is 4. That means we should be able to check this and put a 4 back in for g up here. And we can do this even just quickly in our heads. Let's put a 4 in here. I'll just jot it down above it. Imagine a 4 in there for g. Well, g squared, 4 squared, that would be 16. And then we would multiply it by 3. 16 times 3, that would be 48. And then we'd add 18, 48 and 18. Hey, that brings us back to 66. So a nice way to check your work, put it back in, see if it works out. And here's the cubed question from the first slide. J cubed minus 75 equals 50. We'll tackle this the same way we would as if that little 3 in the corner were not there. How would you get j by itself if that 3 were not there? Well, you would have to add 75 to both sides. So we do that. J cubed minus 75 plus 75. And we got to add 75 to the right as well. The two 75s cancel each other out on the left, leaves us with j cubed. And on the right-hand side, we end up with 125. Now, the j is not by itself yet. It's got this pesky 3 up here. It's got a cube. How do you undo a cube? What's the opposite of cubing? Well, it's to cube root. So we'll take both sides and we will cube root them. So the cube root of j cubed and the cube root of 125. The cube root of j cubed on the left, hey, those just cancel each other out. Again, just like minus 75 and plus 75 up above. J cubed and cube root just leaves you with j. And then we just have to tackle the right-hand side. The cube root of 125. What number, when you multiply by itself 3 times, gives you 125? Well, that would be 5, because 5 times 5 times 5 gives us 125. We can check that, of course, by putting the 5 back in for j up here. Right? If you did that up here, 5 cubed, that'd be 125. 125 subtract 75. Hey, that brings you back to 50. So that all works out. Some of these questions that we've gone through have been perfect squares and perfect cubes. We haven't dealt with gross numbers, let's say, but we could have ended up with, you know, if in our answer here of 125, if that had been 124, we would have had to go for a calculator, and that's the only way to really solve some of those questions. Or if it was the square root of 17, right? There are no whole numbers, right? If you did the square root of 17, you can't say, hey, what number can I multiply by itself to give me 17 without getting a decimal? And it's just going to be a gross decimal that repeats forever and ever and ever, what we would call an irrational number. So those ones you just need a calculator for. There's no way around it. But for the most part, for these questions, if you can get a perfect square or a perfect cube in there, it works out quite nicely like these. Okay, and the last type of problem that we're going to see with squares and cubes are cases where we have formulas that involve squares and cubes. So remember, formulas have multiple variables in them. In this case here, this formula has a v, a pi, which is a symbol that we hopefully maybe should be familiar with, is this Greek letter pi, r, and h. In this case here, this formula in particular tells us the volume, V volume, of a cylinder. So if we had a cylinder over here, imagine like a can of pop, and that cylinder had a particular height. So from here to here, let's say that is the height. And it had a particular radius, so that might be from there to there. Then what would be the volume? How much could you fit into that can of pop, into that cylinder? That's what this formula tells us. But this particular question is telling us that the volume is 156 units. We're not sure what they are. So the volume is 156. That's how much it can hold. The height of this thing is 7. And the question is asking you to solve for r, to isolate r, get it by itself, given these values. So what we'll have to do is we'll have to rewrite our equation, or our formula, but we're going to rewrite it with all of these numbers plugged in. So we're going to write, instead of v, 156. And then instead of pi, we're going to write 3.14. The r squared and h, just to make a quick comment up here, I guess, 2 times 3 times 4. 2 times 3 times 4. That would be 24, right? Notice that it doesn't matter the order that I put the 2 and the 3 and the 4 in. Right? If I had called this 4 times 2 times 3, then we would get the same answer, right? That would still be 24. 4 times 2 is 8. 8 times 3 is 24. We call that the commutative property of multiplication. It doesn't matter the order that we multiply numbers in. So what I like to do with a question like this, when I have pi r squared h, is I like to put my letter, my unknown, at the very end of my statement. So I'm going to rewrite this. Instead of pi r squared h, think of it as pi h r squared, just like the 4 times 2 times 3 and the 2 times 3 times 4. It doesn't matter the order. The reason I'd like to do this is because when I take my 3.14 here, put it back in blue, when I take my 3.14 here, I'm multiplying it by h now. When I have it written this way, h is 7. And then I've got my r squared at the end. And I like having my r squared personally at the end, just like, you would write 3x, not x3, right? So I kind of like having it written this way. Okay, so and another reason I like it this way is because now I see that I can multiply these two numbers together. I can combine the 7 and the 3.14. And when we do that, we get 21.98. So it's 156 equals 21.98 r squared. And remember, these are all multiplied together. So what's happening between the 21.98 and the r squared is it's a multiply. I'll put a little dot here to symbolize multiply, or you can put it in brackets if you like to help separate it that way. Regardless, it's being multiplied, so to get r by itself, to get rid of the 21.98, we would need to do the opposite of multiplying by 21.98, which would be to divide by 21.98. And again, following our rules of algebra, we do that to both sides. So now, on the right-hand side, obviously, the 21.98s cancel out, and it leaves us with an r squared. And now our task is to take 156 and divide it by 21.98. That gives us 7.10. Had to grab a calculator for that one. And then that's r squared equals 7.10. We have one more step left, which is to take the square root of both sides. So we would square root that, square root that. That leaves us with the r value that we're looking for. And when we square root 7.10, we get 2.66. So for a pop can that has a height of 7, a volume of 156, it must have a radius of 2.66. Don't worry too much about what's going on over here with the shapes. Generally, you don't have to memorize equations, formulas like this for volume. Usually those are given to you, but this is what it's referring to, and all the examples in your book, you can see that they have some real-life applications in some sort of geometric setting like this one does. And the last thing I want to share with you are types of equations that cannot be solved that have squares and cubes in them. And what makes these equations here in particular unsolvable for us at this moment is the fact that, okay, well, you want to get x squared by itself. Imagine trying to solve this one. Well, you'd have to move the 3x to the other side. So you'd have x squared equals minus 3x minus 2. And then you'd have to take the square root of both sides. Well, okay, the left side's not too bad. But then the right side, well, what is the square root of negative 3x minus 2? If it was just the square root of 2, yeah, that'd be easy to solve. We could plug that into a calculator. But something like this, we can't take the square root of it. And the reason that these equations can't be solved right now is because they have two terms that have an x with them. And those are currently unsolvable, but when we get to the quadratics unit, we will look at how to solve questions like this. So that's why I bring it up. You're not going to see them anytime soon, but when we get to quadratics, equations like this, we will be able to solve. And same with this one here on the right. This is a cubic function. This one is unsolvable right now as well.